Okay, this is a worked example for a differential equations problem, and this is to do with the population of meerkats. Got a little bit of a difference here. We've got partial fractions involved. Let's have a look. Express 1 over p into 5 minus p in partial fractions. Then it goes on to ask us, tell us that a team of conservationists is studying the population of meerkats on a nature reserve. The population is modelled by differential equation dp dt equals 1/15 p into 5 minus p for t greater than or equal to 0, where p is in thousands. It's the population of meerkats. T is the time measured in years since the study began. Okay, so, and then we're given a boundary condition here, and there's a part B. So let's have a look at part A first. Okay, so we'll just do a partial fractions operation here. We can express this in this form here. If we multiply this out with a common denominator, and then in turn substitute p equals 0 in there, and that gives us a equals a fifth, and then after that p is a fifth, and that gives us b equals 1/5. So quite simply, this partial fractions, this expression here can be written in this form, and might be useful to sort of factorize out that 1/5 there to give us it in this form. So that's a kind of fairly straightforward partial fractions operation. Okay, so that's part A done, and then we go on to the second part, which we've just read out. Team of conservationists. We've got this differential equation here. I've rewritten over there. So it says solve the differential equation. Okay, so we're going to go through our separation process. We're going to get the p's on this side. dp over p into 5 minus p equals dt over 15, then integrate both sides. Now in this process here, what I've done is I've used this form and then multiplied both sides by 5. So this dt over 15 becomes dt over 3, and we're just left with this partial fractions decomposition here. So if we then integrate this left-hand side, we're going to get this. Was that? Now I kind of skipped a step here, really. What we've done here is we've expressed this as the natural log of p over 5 minus p. Then actually exponentiated it and inverted it. So without going into all the details of that, that's given us this equals c times e to the power of minus 1/3 t. Now, if you're not happy with that, I suggest you just have a go through it yourself and see it will actually come into that form. As I say, if you exponentiate it and if you reciprocate it. So we've got, that is the general form of the solution. We've got a boundary condition here, which gives us t equals 0, p equals 1. And if we substitute those in, this side is going to become 4 here, and the right-hand side is going to become c times 1, because if t equals 0, then we've got e to the power of 0, which is 1, so c times 1. So in other words, c equals 4. And therefore our particular solution becomes 5 minus p over p equals 4 times e to the power of minus 1/3 t. Now that's okay, but we kind of needed to be explicit in p, really. So what I've done there, just for convenience, I've called this right-hand side r. Therefore what we've got is if we then, using r, if we then just sort of make it explicit in p, we've got to cross multiply there and then simplify it. So we've got p equals 5 over 1 plus 4 times e to the power of minus 1/3 t. Okay, so again, if you're not completely convinced, just pause the video and just maybe have a go through that yourself. But of course, then that gives us A, B, and C. We can see that it is of this form. We've got an A of 5, a B of 1, and a C of 4. So that's what we've got. And so that basically is the solution to B. Okay, so the solution is actually this equation, but we made it specific with A, B, and C. Right, so if we'll have a look at this equation, we actually inspect it. We see what happens when t increases. As t tends to, well, I guess, larger and larger, because this is a negative power of t, or minus 1/3 t, then this value here is going to get smaller and smaller and smaller, and tend to 0. So 4 times this e to the power of minus 1/3 t will also therefore tend to 0. And the denominator will therefore, in the limits, go to 1. So that's what we've got over here. So the maximum value of p is going to be 5 divided by the 1 plus 4 times 0, which equals 5. And we're talking in thousands. P is in thousands. So the maximum population is 5,000 meerkats, which is what we're asked to show in part C. Okay, so that's really how we've worked it through. It's we need to be on the ball with the partial fractions. Other than that, it's a little bit of messy working, isn't it? All this kind of, kind of reciprocating and stuff like that is a little bit messy. But it's a reasonably typical problem, so you need to kind of practice this sort of thing. Right, okay, so thanks for listening. Hope you found that interesting.